very low dimensions. And so just as a cartoon, imagine that I have a lot of documents, and they're all about sports. And so a couple of things that are cartoonish about this is, this doesn't exist in a two-dimensional space. These are rich, text documents, perhaps. And also imagine that there are actually way, way, way more data points than I have plotted here. And I might notice that actually a lot of my documents that are about sports are actually about football, because it's a very popular sport. And maybe fewer of the documents are about curling. So I don't know if you even remember what curling is. It's that sport where you sort of sweep in front of this disc that's moved, and it's very popular in the Winter Olympics. And anyway, the point is it's less popular right now, and at least for the moment. And so I might say to myself, okay, I want to analyze this data. And oh gosh, there's too much data. And so maybe I could summarize this data to make my algorithm faster. So I might notice that maybe some of these football articles are very similar to each other. And so I could replace maybe some of the similar articles with just a representative article, and I'd give it a really high weight because there were so many football articles to begin with. And similarly, I could replace some of the curling articles with a representative curling article, and maybe I'll give it a lower weight because there weren't so many curling articles to begin with. And so if you've ever run any kind of algorithm on data, you're probably aware that if you run your algorithm on 2 data points, it's going to be super fast. But of course, you want to ask, is it any good? Is this actually something that's helping us in any way? And so this idea of pre-processing data to get a smaller weighted data set and then running some kind of algorithm on it is an old idea. This comes from the computational geometry and theoretical computer science literature. And something that's really exciting about this literature is that they're able to get theoretical guarantees on quality. To say that if I ran on this carefully chosen smaller weighted data set, that somehow it's close to my answer if I ran on the full data set. And so that sounds very exciting, and we'd like to be able to adapt this to something like machine learning. So in particular, the types of problems that people have traditionally focused on in this literature have been more like k-means or minimum bounding box problems. But we have so many more diverse tasks and geometries across machine learning. I mean, just think about all the different types of unsupervised learning, all the different types of supervised learning, classification, regression, hierarchical modeling in these things. We'd like something that can adapt to these diverse tasks and geometries. And ideally in such a way that you don't have to write a whole new research paper every time you want to apply it, that you can just have it automatically and be able to use it. Okay, now people have definitely thought about data summarization before, not just in coresets. So even if we just look at Bayesian inference, which is where this talk is eventually headed, we can find that people have done things like data squashing for Bayesian logistic regression, or if you're at all familiar with the Gaussian processes literature, you've probably heard of inducing point methods, which has a very similar flavor, finding a small collection of data points and running on that. But these have tended to be heuristic in the sense that they don't give us theoretical guarantees on how close we are to if we had run on the full data set. And so we want to ask, could we get something like that? Could we get those guarantees? Now, another thing that you should always think of when you have a ton of data is why not just uniformly subsample that data? And we're going to come back to this question a few different times, but I want to just give sort of a hint of what might go wrong right now. So just imagine that I actually work for a curling manufacturer, and they want me to analyze this data so they can better advertise to their curling clientele. And so I go ahead and I'm like, oh, this is too much data. I'm going to summarize it. How about I uniformly subsample my data? And oops, I lost all of the curling data. Now, you might not be too concerned about that because maybe you're still not convinced that curling is awesome. But you can imagine cases where this really matters. Like, what if I'm in a medical situation and a small proportion of my data are people who have an adverse reaction to a drug? I definitely don't want to uniformly subsample them away. Or maybe I'm in a cybersecurity application and a small proportion of my data is a set of malicious packets on a network. And I don't know those in advance and I don't want to subsample them away. And so there are plenty of cases where we want to keep rare but important data. And so it seems like at least there are some intuitions that maybe uniform subsampling isn't quite cutting it yet. Okay, so we've talked about this sort of high-level intuition of getting at the core of a data set, getting at somehow what's really making this data set tick for our purpose. And so in the rest of the talk, I'm going to start by focusing in more on a particular application, approximate Bayesian inference. So we're going to look at what does that mean, what are we trying to accomplish in approximate Bayesian inference, what's going on there. And then we're going to delve a little bit more deeply into how might we actually construct this core of a data set. So in particular, we'll see in more detail that uniform data subsampling often isn't enough. It'll turn out that, in fact, any type of IID subsampling of our data, even if we're smarter about it, like importance sampling, will also have very similar problems. And we're eventually going to turn to a form of optimization to get the core of the data set, these core sets. And then if there's enough time, I'll talk about another way that we could summarize our data that can also get desirable theoretical guarantees. So in statistics, there's this old venerable idea of a sufficient statistic, which is a nice way to summarize data when it exists, but it often doesn't exist. And so could we approximate it somehow and get something that we can use in other problems? OK, so let's start in on approximate Bayesian inference and what we're trying to accomplish there. OK, so Bayesian inference has been used in many of the major scientific discoveries of the past few years. So if you're familiar with, there was this discovery of exoplanets, 7 planets outside of our solar system. And Bayesian inference was used to get point estimates and uncertainties about candidate observations for these exoplanets and decide, are these, in fact, exoplanets that we're seeing. If we look at the gravitational waves discovery, Bayesian inference was used to get point estimates and uncertainties about the mass and spin of the black hole that was generating these gravitational waves. Tragically, in 2009, an Air France flight crashed in the Atlantic. And one of the big things when a flight crashes is you want to recover the wreckage, and especially the black box, to understand what happened in that crash. And for years, people were just unable to recover the wreckage from this flight. And sort of amazingly, eventually, years later, they brought in somebody practicing Bayesian inference, and they were able to recover it in just a week or two. Traffic routing is a big problem of our time. We have all of this data on different cars, different vehicles, and we want to be able to say, what route should you take, or what route should an ambulance take? And there, if you're going to make a decision about routes, it's really important to not just have point estimates, but also uncertainties, especially if you need some life-saving procedure in a limited amount of time. In understanding microcredit, Bayesian inference is used. So think about microcredit, remember, are these small loans to individuals in impoverished areas, and we want to know, are they effective? And so in trying to assess that, we need to know not just what do we know, but how well do we know it? What's our uncertainty? So this is a reason to use Bayesian inference. Researchers at MIT, like Hamza Balakrishnan, are interested in how much fuel is a plane using based on publicly available information about that plane. And here again, if we're going to actually make decisions based on this, then we really need to know not just, what do we think we know, but how well do we know it. In fishery management, this is a case where we really care about risk, because a lot of times we're seeing that these fish populations are dying out. And so again, we care about uncertainties. And so in all of these cases, we see a sort of recurring theme that these practitioners are really interested in getting an estimate of some phenomenon, as well as an uncertainty about it. Because if you're a scientist or an engineer and you want to make some decision, you want to know not just what do you know, but how well do you know it. Now, of course, there are other reasons to use Bayesian inference. It's interpretable relative to some black box methods. We can pinpoint exactly the things that we're interested in. We can build up these complex models of natural and physical phenomena and social phenomena. And we can incorporate expert information, which is certainly relevant in all of these examples. OK, and just to give a sort of sense of scale here, so there are a number of different probabilistic programming languages for automatically using Bayesian inference at this point. And I think this is a really great development that lets people who are not necessarily experts in this area just automatically use these tools, which is very important for their use. We don't want to have an expert have to devote 6 months of their life to learning about a machine learning tool in order to use it. And so if we look at things like TensorFlow, Stan, Edward, there are many of these. And if we look just at Stan, and just at one among many ways to download Stan, we see that it's being downloaded well over 10,000 times a month. And so these are widely used methods. And I think it's worth asking in all of these cases, are they good? Are we set? Are all of the problems solved in this area? And I would argue that that's not quite the case. So a big challenge with Bayesian inference right now is that there are very well-known methods that can be very slow for users to use. They might have to be waiting around a couple of weeks to get some answers out. And of course, we don't want that to happen. We want them to be able to quickly iterate on their scientific problem. For that matter, also, nobody likes to wait a couple of weeks and then find out there was a bug in their code. But in terms of time, I think it's worth thinking about, there's not just computing time, there's also researcher time. So it's still part of your time if you spent months, tuning parameters or writing down equations just so you can run an algorithm. So we really want methods that, are also easy to use, that are sort of automatic to use, that you don't have to do those things. Now, there are actually plenty of methods that are fast in computing time and fast in user time. In fact, I don't even have to go very far to come up with such a method. I can come up with one right now. Just return the number 5. Done. You've got your answer, right? And it was super fast in computing time. It took no time. It took seconds. We just saw that. It was not tedious. There was no parameter tuning. But of course, it wasn't useful, right? I mean, it's not enough to just be fast. You've got to have something that's reliable, that actually returns something like what you want, like what you're trying to get at in a problem. And so we want something that is fast but reliable at the same time. And that's, I think, where the real challenge lies here. And so our proposal that we're going to explore in this talk is, can we have these data summarization methods, and can that help us get a little bit farther in terms of getting something that's scalable, that's automated to use, that you don't have to sort of derive new equations every time you're going to use it, and that gets, crucially, these error bounds on quality. So for the things that we care about, can we say theoretically that we're going to be close to the right answers? Okay, and so let's think about what that's going to look like. So just to review, in Bayesian inference, we have a collection of unknowns. We're going to collect this in our parameter vector theta. So these are things like, how much is microcredit increasing business profit, and any other unknowns that we have in the problem. And we start off with a prior, a distribution over theta that expresses our knowledge or lack thereof going into the problem. Then we collect some data, let's call it y, and we have our likelihood that relates y to our parameter theta. And then finally, we just apply Bayes' theorem, just a fact of probability, to say what do we know about theta after having seen the data y. Now, just as a sort of running toy example, let's imagine that I have a collection of data. Maybe it's cybersecurity data, so each data point is like a website, and some of the data points are malicious. They're phishing for your personal information. We'd love to know which websites those are. And the other websites are perfectly benign. They're not, doing anything malicious. And so here we imagine that each data point exists at some location, xn. That's the set of features. It doesn't have to be two-dimensional. That's just, we as humans can only see in 2 dimensions, so naturally my cartoons are in 2 dimensions. And then we have some label yn for each of these. And again, the sort of task that we're interested in this case might be something like classification. We want to find a dividing line between these 2 classes. And if we're being Bayesian, we're not just going to get a point estimate for theta, but a whole distribution over theta, which is hard to depict in this graph, and so let me write it over here. This is the kind of thing we're going to get out. This is like a contour plot for our posterior after we've seen the data. But of course, if you've ever worked in Bayesian inference, you know that in any problem that's even moderately complex, we can't just calculate the exact posterior. We have to approximate it somehow. And so traditionally, the way to do this is Markov-Chain Monte Carlo. So this is one of the 10 most influential algorithms of the 20th century. And it's great because we know that if we run it long enough, it will eventually be accurate. The problem with that is that practitioners don't always have until eventually. So they find in practice that it's often a bit too slow for them, and we increasingly see that people instead are turning to modern methods like variational Bayes, especially so-called mean field variational Bayes. So mean field variational Bayes is great because it's so fast. I mean, this is why people are turning to it. It's very fast, it's easy to run, we can make it streaming, we can make it distributed. We've done work showing we can run on millions of documents from Wikipedia with 32 cores in about an hour, and this was back in 2013, so it's only going to be much, much faster now. The problem with mean field variational Bayes is the following. So let's suppose that I look at this exact posterior that I have up here. This is way simpler than anything that we would ever deal with in real life. It's only 2-dimensional. And I apply mean field variational Bayes, and this is the answer. So you don't have to know anything about probability to know that the red thing is not a great approximation for the green thing. In particular, here, we're underestimating the uncertainty, and if we as scientists care about how well do we know something, and we think that Bayesian inference is going to provide a good estimate of that, this is a particularly bad thing to be doing. But it turns out in other cases we can show that, in fact, not only can you arbitrarily badly underestimate the uncertainty, but you can very badly, very, very badly estimate the point estimates, the means. Okay, so we really want something that's both fast but also accurate. Remember, we want something that we can trust. And again, this issue of speed is not confined just to computing time. It's also confined to user time. And so again, something that's been so great about Bayesian inference in the past few years has been this trend towards automation. So we have the no U-turn sampler for STAN, also automatic differentiation variational inference, these very usable tools that mean that people don't have to sort of write down equations for mean field variational Bayes and give sampling anymore. But these still have all of the challenges mentioned above. NUTS is still being used in Markov-Chain Monte Carlo, and so it can still be very slow. ADVI is still mean field variational Bayes typically, and so we can still have these underestimates of uncertainty and bad point estimates. Yeah?
So, is it usually true that mean field underestimates?
So it tends to be true that mean field underestimates. It can actually overestimate, too, which is part of the problem. You don't know which one it is. And I also want to point out that this isn't confined just to mean field variational Bayes. I mean, this is by far and away the type of variational Bayes that is most widely used. But we have a paper where we point out that actually if you're just minimizing the KL and you have a small KL, that doesn't necessarily imply that uncertainties and means are good. In fact, it can imply quite the opposite, that the uncertainties can be arbitrarily far off and the means can be very far off. Okay, so we want to try to deal with this in some way. And in particular, the thing that we're proposing is this data summarization idea. And so let's think about what this might look like for Bayesian inference. So remember, we just said there are two ingredients that go into Bayesian inference. There's the prior and there's the likelihood. Now, if we're going to summarize our data, it's pretty clear this affects exactly one of these ingredients. It's the likelihood, because that's the only place where the data appears. Okay, so let's delve a little bit deeper into the likelihood. Now, up to this point, I've assumed an extremely general likelihood, basically any likelihood. At this line, I'm going to start assuming that our data is independent and conditional on the parameter. This is still extremely general. It's sort of most of the models that I think we typically deal with, but it is a slight assumption, and there are models that don't have this assumption, but we're going to make it anyway starting here. Okay, so if we make this assumption, we can say that the nth log likelihood component, which is the log likelihood for the nth data point, can be written as, we're just going to give it some name, script L sub n. And then the total log likelihood is just going to be the sum over the individual data point log likelihoods. And the idea here is that we want to somehow approximate this with a coreset, as we just said. So what's a coreset? Well, essentially, we're going to be giving a weight to each of our data points. We're going to give weight 1 to data point 1, W2 to data point 2, weight W3 to data point 3, and we'll collect this vector of weights as the vector W. And what we want for W is that most of the elements of W should be 0. So this 0 norm of W, the number of non-zero components of W, should be much less than the full size of the data set N. And then once we do that, we can form our likelihood approximation as a sparse sum of the individual log likelihoods. It's sparse because most of these W's, again, are 0. Now, we don't want it to just be sparse. We also want it to be a good approximation, that somehow this coreset log likelihood should look like our exact log likelihood. And so to make that precise, we're going to do two things. So the first is to say, let's suppose that we imagine these likelihoods, they're these infinite dimensional functions. Let's imagine them as something we can put a Hilbert norm over. And so if we define such a norm, then we'll say that we have sort of an epsilon good coreset if that norm is sufficiently small. So all of the theory that I'm going to have going forward from here for saying that these likelihoods are close, this likelihood approximation is close, will be for a sort of arbitrary norm that we might have chosen. But if we want to get guarantees of the form that I was talking about, guarantees on point estimates and uncertainties, it'll help to actually choose a specific norm. And so in particular, we show in this paper that if we choose a weighted Fisher information norm, we can get a bound on the Wasserstein distance between the exact posterior and the approximating posterior. And it's for 1 and 2 Wasserstein. And so we can show that we can get a bound between the exact posterior mean and variance and other uncertainty estimates and the approximating posterior mean and variance and other uncertainty estimates, which is what we were aiming for. We wanted to get some theory that told us that our approximations are close to what we're really reporting. Okay, so what does this slide do for you? It does nothing. It doesn't tell you how to make such a coreset. It says, hey, this is what we'd like. It's like a wish list. This slide is what we want in life. But now we have to think about how could we make it. Yeah.
So just to make sure I understand what might be a limitation here, the Wasserstein distance metric is looking at whatever you want to test to make a mean out. So it is to some degree task specific. If you're interested in how long, something like the probability that somebody's going to die before the ambulance gets there, in the example you gave before.
Yeah, so I would say
a different metric, and so you do need some task.
So I'd say there's two different things going on here. So I'm totally on board with your task specific point, but I think that the task specific part is coming in via the likelihood, and then the Wasserstein is just a really nice metric for getting bounds on means and the uncertainty differences, and so that's what we're using the Wasserstein for. And I want to emphasize this task specific point and how I think we really need to encode it. So let's imagine for a second that I have a classroom, and maybe 90 people in this classroom have studied for the test, and 10 people have not. And I want to do some analysis over these people, and I want to run coresets first. I mean, imagine it's a large enough classroom that you actually feel like you need to run coresets. And And so what I'm going to do is I want to choose the coresets such that they summarize these 10 people who haven't studied and these 90 people who have studied. Now let's imagine now that I'm doing a different analysis on this class. That 10 people got the flu recently and 90 people did not. It's probably not the same 10 people that didn't study, although those could be correlated, but forget about that for the second. And now if I want to do some analysis about health outcomes, I really want to summarize these 10 people who got the flu separately from the 90 people who did not. And so I guess the point that I want to make here is that we don't want a method that's just going to choose our data points without keeping the task in mind, because that task should really matter for how we summarize. We're not going to get this like rare but important data that we were talking about if we don't keep that task in mind. So I totally agree with you about the task, but I think that that's coming in via the likelihood.
So the Wasserstein distance requires a distance in theta space.
No. Oh, so something I should be really careful about is these are both functions of theta. And so this is a norm sort of over functions, comparing functions. Oh, yeah, OK.
Yeah. But there's an underlying metric that the Wasserstein, so it's like an Earth mover's distance thing, right?
Yeah, yeah.
And so you need to say how far did the Earth get moved?
Yeah.
You get moved from theta is 2.0 to theta is 2.4.
So yeah, so I would say it's a metric over distributions over theta space, which are the posterior.
That's right.
Yeah.
But you need some underlying metric on theta space in order to define the Wasserstein distance.
Oh, sure,
And
yeah.
That's what I was thinking would be task specific, because you may not actually care about estimating the thetas. You might care about estimating some downstream estimate of the theta. Sorry, some downstream consequence of the thetas, like the probability that they, given these thetas, that they die before they get to the hospital.
Yeah, yeah. So here we're specifically looking at things like posterior mean invariance, and so that is why that is sort of the one aspect of the downstream that you could be thinking about that we are interested in. If we were interested in something that was fundamentally different from that, then we would have to prove that either the Wasserstein implies that or our fundamental metric over here implies that. But I think the likelihood also encodes the task. Let's at least put it that way.
Fair enough.
Okay. Cool. Yeah. Right, so Wasserstein is essentially this Earth mover's distance, like how much sort of mass do we have to move to get to another distribution, and because of that, let me point this out on another higher level. So a really natural distance that I think we're using all the time is KL divergence. So callback-Leibler divergence is used in machine learning for everything, certainly for approximate Bayesian inference. And the reason that we're using callback-Leibler divergence is that it just happens to get rid of the normalizing constant. When we use it in the direction that's used for variational Bayes, it happens to just get rid of the normalizing constant in the posterior. But it doesn't have implicit in it, in fact, it definitely doesn't, we can have counterexamples, any notion of distance that's relevant to means and variances. And so if that's what we care about, it's a convenient distance, but it's not the distance that's getting those guarantees. So Wasserstein, by getting at the sort of Earth movers idea, is getting at those guarantees. Conversely, though, it's not a convenient distance. You don't get rid of this nice normalizing constant. And so by using this weighted Fisher information distance, we get something that gets rid of the normalizing constant that's convenient, but still bounds Wasserstein. Yeah.
So theta, you haven't quite said what it is. If you can discrete, it could be continuous.
Yeah.
And so then that epsilon coreset definition, that norm involves an integral over theta.
Yeah, yeah.
I think that's what Jason meant, that it needs some kind of notion of, I don't know whether you call it a metric, but basically you're defining an integral, so some kind of measure of it.
Yeah. So if we use a weighted Fisher information distance, like the one I'm talking about, it's an expectation over some weighting function over theta of this difference as functions of theta. And so, yeah, so any reasonable norm that you use here for most tasks that we would be dealing with are going to be some kind of expectation over theta. Yeah.
So for the record, I have a better way of phrasing what I was asking. Basically, I meant I don't care about the posterior mean of some parameters, which depends on the parameterization. Yeah. I care about low regret in the decision I make, given those parameters. So if the decisions or the loss of the decision is a continuous function of the parameters, then being close here implies being close there. But sometimes there are discontinuities, and that's why I was giving the ambulance example, because there's a difference between just making it to the hospital on time and missing it by an instant.
Right. And I guess the meta point that I want to make in all of this is that we should have something that makes these guarantees, or that says how close we are, and that's not currently the case.
Yeah, it's great to have guarantees. So
cool.
You should tell us about them.
Yeah, great. Okay, how are we going to actually make this set? So that's where we're going next. So in particular, we're going to start thinking about how could we actually come up with this summarization. And again, I think the first thing that we should always think is why not uniform data subsampling? Because if it works, that's great, because it's so simple and fast. Okay, so why not uniform data subsampling? Well, let's again think about the issue that we just brought up. Hey, I have all this data and I uniformly subsample it, and oops, I lost some really important data. Now, I want to emphasize, if you have a two-class classification problem, of course you're not going to uniformly subsample away one of your classes. But you can imagine that maybe you have two important types of phishing data and you could subsample away one of them. And that would be really bad, and you wouldn't know it in advance. And in fact, there's actually a much more subtle and related problem that's the following. So here's my data. And suppose that I uniformly subsample it and I have at least one representative from each class, so I can upweight it so it looks like the full data set. I can run approximate Bayesian inference on this data set. I can get a full posterior by doing that, like maybe I run MCMC, and I'm just going to plot the mean. And now I say to you, hey, this is the cool thing that we're all doing right now. How about you do the same thing? So you on your computer uniformly subsample this data set. You run approximate Bayesian inference. You plot just the posterior mean approximation that you get. And then you convince your friend that this is the cool thing that we're all doing right now. And so they run uniform data subsampling. We all have different random seeds, so we get different data subsamples. They run posterior Bayesian inference, and they plot their approximate mean. And the point that I want to make here is you don't have to know ground truth right now to know that these are bad estimates, because they don't even agree with each other. And in fact, this isn't just a cartoon. This is something that we see in an actual data analysis. So here we have 10,000 data points that are labeled blue and red. We uniformly subsample 10 of them, m equals 10. We upweight them so they have the weight of the full data set. We run Bayesian posterior inference. We plot the posterior mean, and we do this 49 more times. And so we have 50 different runs of this. And we see that they don't agree with each other at all, that these are really bad estimates of the posterior mean. And this is not something that we would trust in general. Not to mention that this is an extremely simple problem. It's just Bayesian logistic regression. And so we think that we should actually have a much better summary of this. Now, of course, if you increase the number of data points that you uniformly subsample, you get much less uncertainty. But that's not the point. You don't want to run on almost the full data set, 1,000 data points, especially for such a simple problem. You want to be able to run on 10 data points, because that'll make your MCMC super fast. OK, so it seems like uniform data subsampling isn't cutting it. Is there something else that we could do? Well, we might think to ourselves, hey, we know that there's part of this data that's really important, the phishing data. That's what we really care about. Maybe we should just upweight the phishing data to get an estimate of what's going on. And so we say to ourselves, hey, what we'd like to do is we'd like to run on the full data and approximate our posterior, but we can't do that because it's too expensive. We'd like to run on this great coreset that summarizes our data such that when we run on it, we approximate the full posterior. How do we make that coreset? So here's a proposal. Let's take our data set and let's upweight the phishing data. We know that the phishing data is really important in this particular example. And now we sample according to these weights rather than uniformly subsample. So in particular, we expect that we'll get one of the benign websites just because there were so many of them, and we expect that we'll get one of the phishing websites because they had such high weight. Now finally, notice that unlike the coreset that we've been talking about this whole time, the weights are sort of inverted here. There's too much weight on phishing and too little weight on the benign, and so we'll invert these weights. Okay, so it turns out that in fact, if you do this, and then we can form this approximation like follows, we can actually solve for what's the optimal set of importance weights. What do I mean by optimal? I mean we're going to get close in whatever Hilbert norm we've chosen. And so it turns out this optimal set of importance weights is such that they are proportional to the Hilbert norm applied to the log likelihood for that data point. And so if we just write the normalizing constant, we'll get the sum. And so I just want to recap what we're doing here. We start off with our set of data. We calculate these optimal importance weights. We sample from the optimal importance weight, so we're only left with a few data points. And then finally, we invert the weights. OK, now we want to ask, is this any good? And this is a little bit more complex than just the uniform data subsampling case. OK, so here's what we can say. We can say that with high probability, this error, the coreset log likelihood error that we talked about before, is bounded by sigma. That's the normalizing constant that I just described. Eta bar is a notion of how well aligned the different log likelihoods are. This comes from this high probability bound, so it's high probability because we're importance sampling. And then finally, we have the square root of m bound. OK, so on the plus side, as m increases to infinity, this bound goes to 0, so it's not totally silly. On the minus side, square root of m is actually just exactly the Monte Carlo error rate. So that's no different than uniform subsampling, and so that's pretty disappointing. And in fact, we see this in practice too. So here we do importance sampling. We have our 10,000 data points as before, Bayesian logistic regression as before. We importance sample now our 10 data points in black. We run Bayesian posterior inference. We plot the 50 posterior means over 50 different runs. And we see that, again, they're just unacceptably noisy. Like, this would not be a good estimate. And we could get it with high probability, and we wouldn't know that anything else had happened. Now, we could increase the number of points that we importance sample, but again, that's not the point. Sure, it gets better when we get 1,000 importance sampled points, but we want to have 10. We want to have very few points so we can run something that's very fast. And so it seems like somehow what's going wrong here is that IID sampling is failing us. And we want to ask why that is. OK, so let's think about, again, our goal here is to somehow minimize this error between the coreset log likelihood and the exact log likelihood, subject to these restrictions. And so let's look at an extremely simple data set. Like, this is about as simple as it gets for continuous data. So our yn are just one-dimensional. This is our data. And because it's one-dimensional, if we have a Gaussian model, we can just plot that density right above our individual log likelihood. Or so we can plot our log likelihoods above each data point. So that's what we're doing here. And we do this for every data point. And then we have a scaled version of the exact log likelihoods here. Scaled because if we scale in these W's, it doesn't matter. And the goal here is that we want to find a small weighted version of these individual log likelihoods that approximates this exact log likelihood, this exact likelihood. And in fact, there's a great coreset of size 1 here. Just choose a really central point, and the black curve will look just like the blue curve. Now, why are there weights on these lines? Some of them are thicker than other ones. That's because these are the importance sampling weights. And so we see that importance sampling is doing the opposite of what we want. It's not picking this thing right in the middle. It's picking the likelihoods way out to the side. OK, let's think of an even simpler way to visualize what's going on. Effectively, once we have this norm, everything's like a vector. And so every log likelihood is like a vector. We're summing them all up to get the total log likelihood vector. And now we want a sparse vector sum of these vectors to approximate the thing in blue. And so there's a great sparse vector sum of size 1. Just take one of these vectors here and give it a huge weight, and you're very close. So why don't we just importance sample with all of our weight there? Because we're never going to do any better than that vector. We'll only ever be right here. And what we really want to do is we want to say, hey, this is the most well-aligned vector. Let's choose this vector. And then let's choose something that's well-aligned with the residual. And then let's choose something that's well-aligned with that residual. And so the real problem here is that we're not considering residual error direction. Now, we could possibly have some kind of adaptive sampling algorithm, but it certainly looks at this point like sparse optimization is a good idea. That we really want to find like the best vector at every step. Yeah?
So the adaptive sampling algorithm would be something like herding, is that right?
It could be. We didn't explore it. It's more like, I think it would just be like importance sampling, but where the distributions change.
Right, so herding is this idea of sort of trying to incrementally construct a coreset, and it's not IID.
Yeah.
So maybe you'll say something.
I think there could be connections, but I'm just going to go ahead and go with the sparse optimization, and we're going to find that we get an exponential convergence, and that's all we want. I think that if you can do well with sparse optimization, that in this case, that actually sampling isn't really going to buy you anything because you're just going to get a high probability bound rather than a not, just a straight bound. Okay. Yeah.
How do you get the importance sampling weights again?
So I didn't explain exactly, but we can show that this particular set is optimal in the sense that if you were trying to approximate your exact log likelihood with this coreset log likelihood, that this will give you the best approximation for that, for whatever Hilbert norm that you've chosen. Incidentally, the theory that I'm showing here is agnostic to whatever norm that you want. It's just that there's that second step if you're interested in point estimates and uncertainties. And so what I'm plotting here is if you chose those optimal importance sampling weights, what would they be? And it turns out that these are those optimal weights. But the fundamental issue isn't sort of the importance sampling weights, it's this non-adaptivity. It's the fact that you can't update your weights based on where you are, based on what you've seen so far. I'll briefly note, herding does not get the exponential convergence that we get too. So it's just, yeah. But I don't know off the top of my head if I have a really good explanation for why that difference is there. But it's still polynomial convergence.
Right. You're right that there's no reason to do sampling.
Yeah. If we can do optimization, which we're about to find out. We can. OK. Let's try out this optimization. So nowadays, when you hear sparse optimization, I think the first thing that comes to mind is the Frank-Wolfe algorithm. So let's just review what that is. So Frank-Wolfe is what we would like to use if we're interested in sparse optimization of the following form. We want to do convex optimization over a polytope D. So here's a potential convex function that we might be interested in, this f here, and we're interested in optimizing over x in our polytope D. Okay, so how does Frank-Wolfe work? Well, the first thing we do is we say, hey, let's choose whatever is the best vertex, like that minimizes the f just over the vertices. And now we're going to iterate on the following steps. We're going to say, hey, whatever point we're at right now, like maybe this point, let's go up to f and find the gradient of f. So that's going to be some hyperplane like this brown hyperplane over here. Now over that hyperplane, let's find the minimizing point in D. So we're kind of using this as an approximation to our function. Because we're minimizing a hyperplane over a polytope, that's got to be a vertex. And then finally, we do a line search between our current point and that minimizing vertex. And so you'll notice that we start at a vertex. Then we do a convex combination with another vertex. Then we do a convex combination with another vertex. And we keep doing this. And so that means that our answer, after we've run this algorithm for m-1 steps, will be a convex combination of m vertices. And so that's the sparsity of Frank-Wolfe, that we can express our answer just in terms of m vertices after m-1 steps. Okay, so that seems pretty nice. So in particular, actually, the thing that I want to emphasize is this sounds like it would be perfect for our problem if we could put it into the form of Frank-Wolfe, right? So if our vertices basically represented the data points, then we'd pick up m data points, m coreset points, by running Frank-Wolfe for m-1 steps, if we can put it into this form. So let's ask, can we put it into this form? So we can minimize this norm, or we can minimize the squared norm. It doesn't matter if we're just trying to find these w's. And you might say to yourself, gosh, I've minimized a likelihood before in my life, or I've maximized a likelihood, minimized a log likelihood. And I know that's not convex. That's never a convex problem. But you've been optimizing in theta. This problem is linear in W. And so it's just convex in W overall. I mean to say this is linear in W as a function, and so the whole problem is convex in W. So that's awesome. Convex optimization is the best. What about this constraint set? This is definitely not a polytope. This zero norm is really killing us if we want a polytope. But what we can do is we can just invent a polytope. If we invent a polytope where each data point, each vertex is a data point, then after running Frank-Wolfe for m-1 steps, we'll automatically satisfy this constraint. It's not a relaxation what we're doing. We're just saying that by running Frank-Wolfe for a limited number of steps, we get the satisfaction. And so we can create such a polytope. Here's just one polytope. It doesn't even have to be the only polytope. In fact, I'm sure it's not. You could just come up with another one. And this is a polytope such that the original data set with all the weights, just one, will satisfy this because this sigma is just defined to be the sum of the sigma n's. This is from the importance sampling weights before. And each data point effectively forms a vertex. And so by using this, we can show that just by running for m iterations, we're able to get that our error now has a bound that decreases exponentially in m. Okay, so that sounds nice in theory. Of course, we still want to check, is it good in practice? So that's what we'll do next. Okay, let's start with an extremely simple problem, a conjugate Gaussian model. Why would we ever look at conjugate models? Because we know ground truth. Those are the only models where we can actually compare directly to ground truth without some approximation. And so here we have 1,000 data points in gray. So those are the little gray dots. The exact posterior predictive mean is this blue dot, and posterior predictive uncertainty, 3 sigma interval is, or region, is this blue circle. Now what we're going to do is we're going to uniform subsample 5 data points. We'll plot our approximations in green, and we'll do this 50 times. And again, it's really noisy for a really simple problem. Sure, it gets better as we increase the number of points that we subsample, but that's not the point. We want it to be really good for very few data points. And we see the same problem with subsampling, with importance sampling. That we still get this very, very noisy case. And again, we think this should be really simple. We should just have a coreset of size 1 for such a simple problem. And in fact, that's basically what we see with Frank-Wolfe. So again, we're running 50 times, but you can't see the difference between the green and the blue in this case, because there's so much in agreement. And that's because it's doing the smart thing. It's taking a point that's very centrally located, and it's giving it a ton of weight. And sure, it gets better as we increase the number of points, but we really want a tiny coreset. We want to run on 5 data points, not on 500. Is there a question?
Can you
So for Frank-Wolfe, it's decreasing as alpha to the m for a constant alpha. Yeah, plus square root of m, but that's just more decrease. The decrease is still exponential. Well, no, the decrease will be dominated by the exponential. When you have an exponential plus a polynomial, the exponential will kick in. Cool.
I mean, if I n as alpha is 0.1.
Yeah.
He's thinking alpha less than.
Oh no, alpha is greater than 1. Yeah, because otherwise it wouldn't even decrease. Yeah. Yeah, I agree with that. But no, alpha is definitely greater than 1 in the denominator. Yeah. Yeah. Yeah, strictly. And in fact, we can show that it's strictly greater than 1. Yeah. So it's definitely going to be a decrease. Agreed. Okay, so this is some toy problem. Let's look at, before we move on, let's also just talk about, we can actually, in this case, calculate the KL divergence between the approximate posterior with the coreset and the exact posterior. And here we're just approximating with the coreset because everything's closed form, which is nice. And we can see that random subsampling, uniform subsampling, importance sampling, these all have orders of magnitude worse error than Frank-Wolfe coresets, which is here in blue, for all of the number of coreset points m. Okay, so let's go back to this logistic regression problem that we saw before. So these first two rows are exactly what we saw before. Nothing has changed. And now we're running Frank-Wolfe. And so a couple of things to notice. One, the error here, the sort of noise that we get over 50 different runs, is less than 50 different runs for m equals 1,000. So that's desirable. The other thing that I think is really interesting is look at the geometry of this problem. That it's automatically, we didn't have to come up with a new algorithm for every different logistic regression or Poisson regression or whatever. We just run the Hilbert coresets algorithm. It's automatically picking up that this geometry is unique. That's finding this point that's sort of perpendicular to this dividing line, and it's giving it a really high weight. And then it's finding some other points to correct that. But I think what this is pointing out is that, again, for each different problem, for each different task, there's sort of, you want to get the summarization for that task. Like if we had used k-means clustering here, we would just get some points in the middle. We wouldn't necessarily get something that picks up this geometry. Yeah?
I know you're showing us n equals 10 there. What would it pick for n equals 2 or 3?
Oh, that's interesting.
Almost perpendicular.
So I'll make a quick note. So I actually don't get all the way up to m equals n. So the total n is 10,000 here. So it's still actually less. So I'm not even sure actually what it would do for m equals n. It certainly wouldn't choose.
M equals 2 or 3.
Oh, I see. For fewer. Yeah.
I think the choice of going to the right was arbitrary. You could have picked something on the left given its height.
Yeah. So I feel reasonably confident saying that for m equals 2, it's definitely going to have to pick up something from each of the different classes. But beyond that, I don't know off the top of my head. I would suspect that it's going to pick up like probably these 2 points just to balance. But well, the rate will be the same. Will the performance be very good? So it turns out, I'm not going to talk about this too much. It turns out that Frank-Wolfe does have a problem. And the problem is the following. We are approximating our convex function with a hyperplane to run Frank-Wolfe. And so in particular, if you have a data point in your polytope that's way over here, then when you approximate your convex function, even if it's just right here with this polytope, the best point is going to be over here because it really minimizes that polytope just over this approximating hyperplane. And so there's a real scale issue with Frank-Wolfe, and it turns out that if we correct this scale issue, which we do in a follow-up paper, that you can get much better performance for a very small number of points. So you still have the exponential rate, but you get much better performance for a small number of points. Yes, yeah. Well, it affects the alpha, but it's more than that. It affects if you recall, there was a constant, and then it was divided by alpha to the m plus square root of m, something like that. It affects the constant. And so in particular, the bound that we get for Frank-Wolfe is proportional in the numerator to the sigma, which is the sum over the Hilbert norms applied to the individual log likelihoods. And it turns out what we really want is a bound that is proportional to the total log likelihood. It's like the difference between taking the absolute value before you do the sum versus taking the absolute value after you do the sum. And so we can get a better bound like that by basically fixing this problem with Frank-Wolfe. And I'll show a graph of that shortly. Okay, we do this on a bunch of other models, Poisson regression. We actually do clustering on a sphere, and I'll encourage you to check those out in the paper. Basically, we just see the same motif over and over again, that these are very noisy, and that if we do Frank-Wolfe, we get a lot less noise. Okay, here's something that you should be very concerned about. Frank-Wolfe takes a lot more time to run than uniform subsampling. And so actually, is that worth it? What you really want to do is say, what's the total amount of time where you run your coreset pre-processing step and then your inference algorithm, and is that total amount of time worth it? Because uniform subsampling is super fast. And so what we're showing here is total amount of time, total CPU time, so we want to be lower over here, and total error, so we want to be low over here. I mean, I don't know, I emphasize total there, it's just error. Right here, for the moment, we're comparing just uniform subsampling and Frank-Wolfe coresets, and the way we're getting aligned is that for each of these data sets, as well as 2 simulated data sets, we're increasing the number of coreset points. And so we see that as we increase the number of coreset points, these are log scales, we're getting orders of magnitude better, but for a small number of coreset points, we're actually not doing that much better. And we fix this with exactly the method that we were just talking about. And we call it greedy iterative geodesic ascent. The geodesic comes from doing the proper scaling on the optimization problem. But essentially, we still have the same framework. We just use a different optimization problem. And we can get orders of magnitude better even for a very small number of points, a small number of coreset points. OK, so if there's enough time left, I'm just going to mention another way that we could summarize data. Okay, so there's this idea of sufficient statistics, right, from the statistics literature. I'll be much faster in this one. So it's great when we have sufficient statistics, but we often don't have them. Can we approximate them? So let me just recall, what's so nice about exponential family likelihoods? And I'm not talking about conjugate families. I'm just talking about, just suppose your likelihood is exponential family. Well, what's really nice about it is, so suppose we have exponential family likelihoods. So we have our data, points 1 through n, they're conditional on some covariates perhaps, and we have a theta. And so if we have an exponential family likelihood, we can write the probability of this data as exponential of some function that depends only on the data, the y-n's and x-n's, and some function that depends only on the parameter. Now you might also be thinking, hey, where's the normalizing constant? But that falls into this as well. It's just a -1 here. Also, it depends only on the data. Okay, so what's nice about this is that we can write this whole likelihood, this whole product, now as an exponential of a sum of just the data times something that we multiply at the end that just depends on the parameter. And so why is this nice? Well, let's think about how Markov-Chain Monte Carlo would typically run. You're at some particular parameter value. Now you look at another parameter value and think about going there. You calculate the likelihood at that parameter value. And now what are you going to have to do? Well, normally you'd have to go through every data point to calculate the likelihood. But in this case, you could have pre-processed and just calculated this whole sum. And now when you look at a new parameter value, you just have to do this dot product. And as long as it's not too high dimensional or too crazy, this will be a lot faster. And so when you have an exponential family likelihood, your life is great. You have a very scalable algorithm. You can just pass through your data once. You can trivially make it streaming by just adding new data points. You can make it distributed by just doing addition over different data points at different processors and then combining it. And it's very complementary to MCMC. But the problem is that we often don't have these sufficient statistics. So if we think about generalized linear models, deeper models, hierarchical models, we often don't have these. And so we propose, why not have some kind of approximate notion of a sufficient statistic? And in particular, our proposal is to use a polynomial because we know a lot about how well it approximates things. And the monomials can be sufficient statistics. Okay, so if we do this, we can look at some advertising data that's freely available online, which is the nice thing about it. We look at 6 million data points and 1,000 features. This would traditionally be a pretty challenging problem for a Bayesian method. We have a method that's streaming, distributed with minimal communication. We can run on 22 cores on this whole data set in just 16 seconds, which is very desirable. We get some guarantees on Wasserstein distance. I think these aren't quite as nice as with coresets, where we can really control this error in this nice exponential way as we increase the number of points. But we can get some really nice performance on some simple problems. Okay, so just to summarize, we've explored a couple of methods for data summarization. And I think what's nice about these methods is that they're scalable, that we do get these big speedups, that they're automatic. I mean, in particular, the coresets method is very automatic, that you can have this likelihood and you get this method that's going to work for that likelihood. And you're going to get these error bounds on quality for the things that you're actually reporting as a practitioner, the means, the uncertainties of your posterior. I'll also just emphasize this point that I didn't emphasize too much before, which is that you have this knob, this computational statistical trade-off knob, which is you add more coreset points to get more accurate for more computation investment. Okay, so we talked about coresets and approximate sufficient statistics. I don't think this has to be the end of the data summarization story. Surely there are other ways that we can summarize our data, and I think that would be really interesting to think about. In fact, I think this is a start in other ways. I mean, just the fact that by making a sort of more careful version of our optimization problem, more carefully optimizing this, we got these big speed-ups. I don't think that's going to be the end of that. Probably there are a lot of other smarter things that we could do to get way better performance. Okay, so if you're interested in this work, let me just point out a couple of relevant papers. So if you read only one paper that is basically describing the setup that I talked about here, this is the one. This Hilbert coresets framework, the framework that I described today, this paper describes that. If you're interested in the speed up, this sort of much better speed up using a more careful construction algorithm, that's this greedy iterative geodesic ascent here. We had a very early paper where we first started thinking about coresets for Bayesian inference. That's here. But I think then we really made it much more general with this bolded paper earlier. And if you're interested in this idea of approximate sufficient statistics, that's this other paper in bold here. Thank you. Yeah.
First of all, thanks for the nice talk. And the question I'm interested in how this measure can be scaled up to settings where the likelihood is out of some more complicated function family, for example, a neural one. At least in this talk, I didn't see any reason why it should.
Yeah, so in theory, I don't think there's any reason why it shouldn't, but I will note this. So there is a very real sense in which if you want end-to-end pipeline theoretical guarantees, then you need not just our theoretical guarantees, but you also need guarantees of the form of, when I run approximate Bayesian inference, that's going to give me a good point estimate or uncertainty. And so I think you can definitely apply this to a Bayesian neural net, but to get something like a theoretical guarantee, I think we just don't have those for Bayesian neural nets, for MCMC, for VB, for any of these things. I just don't think there's any realistically practical sense or theoretically particular sense that says that we're actually getting close to that exact posterior.
So my takeaway is you think it's definitely possible to try this on your models, but what we lose is the theoretical guarantee, right?
So I think for sure you're going to lose the theoretical guarantee, and I think there's probably more that could be done to, just as we got that big scale up by doing Giga, I wouldn't be surprised if when you're dealing with these deeper hierarchical models that there's something smarter that you could do that would get you closer, but absolutely, I think there's nothing in theory that keeps you from running this for an arbitrary likelihood.
Okay, thanks.
Oh, yeah. Oh, yeah, there's over here.
So you talked about the error bounds you can get with this method. Maybe I'm imagining this one. What do those actually look like for, say, the simple example? So you have two classes and wow, all the means are like right there. But what's actually the error bound?
Yeah. So I think a great question here is, let's see some actual numbers. Like, what is the actual constants here and the error bounds that you're going to get? And we don't have those. We need to get them, and I think it's totally the right set of questions. And I want to say that we're going to get that soon. Hopefully that's true. But right now we don't have that right now. We just have hey, there's this nice exponential convergence. Hey, you get this much better performance with Giga. But I can't give you some direct numbers for this. But I think absolutely that's the right next direction. Yeah.
Question, I think. But now thinking about the alpha that goes into your bound.
Yeah.
And I was thinking, when is it large, when is it small, and perhaps how it might relate to, I don't know, maybe the Fisher information or something about.
Right. Yeah. So I can tell you what.
The difficulty of the problem.
Right. So I'm gonna tell you the base of the exponential function with Frank-Wolfe. It's actually a little bit different for Giga, obviously, but maybe we can just examine the Frank-Wolfe. So what we have here is it's, if I recall correctly, something like this. So it's 1 minus r squared sigma squared over eta bar squared. Sigma squared is the sum of the norms of the individual log likelihood components. So it's a notion of the scale of the problem. Again, it's kind of the wrong notion. We got to a better one with Giga, but it's the notion that we use with Frank-Wolfe. Eta bar is the max over the log likelihoods, the difference between any two log likelihoods normalized by their size. And so it's sort of like what's the farthest away things are if we don't include the size. And then r squared is the distance between the exact log likelihood, if I recall correctly, and the polytope that is formed by making these guys the vertices. And so we can prove that this is definitely going to be less than 1 in general, because all these scalings sort of cancel out. If they don't cancel out, it's because I wrote something wrong on the board. But if you check in the paper, they cancel out. But I think this is correct. And so somehow it's this distance between the actual log likelihood and like sort of this edges of the polytope. And so that's kind of the constant that we're dealing with Frank-Wolfe. Again, it's something a little bit different for Giga, but this is like the scale for Frank-Wolfe. Yeah.
So Frank-Wolfe is conditional with 80%, so you get, and your objective is nice.
Yeah, exactly. And because we wouldn't normally get these really nice exponential guarantees for Frank-Wolfe, but our objective is so nice.
But the constraint set is not convex.
Yeah. Yeah, and so it's really, so the constraint set is not only non-convex. I mean, the original constraint set is not even a polytope. And so I do want to emphasize how much we just pulled this polytope out. We're like, here's a polytope where each data point is a vertex. And what's great about Frank-Wolfe is that in some sense that's all you need. That you just need to create such a polytope, and then by running Frank-Wolfe, you satisfy this fundamentally extremely hard zero norm constraint without doing any relaxation or any weird stuff like that. Like, that's incredibly powerful. But I think conversely, because we sort of arbitrarily made this polytope and arbitrarily chose Frank-Wolfe, that suggests that there are a lot of better things that we could do. I mean, Giga is one of them, but I suspect there's a lot more.
So I'm wondering about connections to, or maybe I should say generalizations to active learning.
Oh, yeah,
you're
yeah.
doing optimization to find points that are informative because they're near the boundary.
Right.
Now, for that, you need the labels. And
Yeah.
in the case of active learning, you don't have the labels, so you can't compute the likelihood. Could you
Yeah.
still do it with value of information or something?
It sounds super interesting, and I suspect that there's something there. And I don't know that I can say too much more than just that. Like, yeah, I've also wondered about this, but not to the extent that I have a solution that I can tell you about. But yeah, I think that's a great idea.
It's surprising that you solve this sparse optimization problem without making any assumption. You can find a solution which has support only on log 1 or epsilon point.
Well, okay, so I would say that there's a lot of assumptions or constraints that are implicit in our problem. So one is, the thing that we're trying to approximate is exactly the sum of the things we're trying to approximate it with. And so like there's a lot of regularity that just comes from that. And then on top of that, the W's that we're optimizing over, we essentially have this quadratic problem. And so it's just everything can be done in like unusually closed form, that you get these really nice things. I think this makes it a much simpler problem than something where it's like, oh, how do I approximate something that's arbitrary with this set of points? Like, we're not doing that. We're only approximating something that is literally the sum of this set of points. I guess I think that it's due to the special form of this problem that the answer really is the sum of the individual components. But I'm totally willing to believe that there's something deeper going on there that's specific here.